Welcome to Wisdom Docs. Somewhere in eastern Washington around 17 million years ago, the ground cracked open along a line of fissures and began to pour. Not in a single mountain, not in a cone you could draw or name, but along long seams in the earth, like a wound that would not close. And out of those seams came lava. Quiet at first, perhaps. A slow welling of molten rock, dark and heavy, glowing where it broke the surface and cooling to a black crust at its edges. And then more still, until the land could not hold it, and the lava began to move. It moved west. It moved across what is now the Columbia Plateau, across country that had its own rivers and its own hills and its own slow life, and it buried all of it under a tide of stone that was still hot, still liquid at its heart, still flowing. And it did not stop at the next valley, it did not stop at the hills. It poured on hundreds of kilometers, a single flow of lava traveling from the country near Idaho and eastern Washington all the way to the edge of the continent, all the way to the Pacific Ocean, over 500 kilometers, one flow, one eruption, and it reached the sea while it was still molten, still moving, still warm enough to glow. Think about that for a moment, slowly, the way you would turn a smooth stone over in your hand in the dark. 500 kilometers is a distance that would take you the better part of a day to drive on good roads without stopping. And this was lava. This was rock that had melted deep below the ground and risen and spread itself across an entire landscape in a matter of days, perhaps a few weeks, as a single sheet, and it covered everything it touched, and where it met the cold water of the ocean, it would have steamed and hissed and finally hardened into the black, stair-stepped cliffs that geologists climb over today, looking for the story written in the layers. That single flow is part of something called the Columbia River Basalt Group, and it is one of the youngest and best preserved features of its kind anywhere on Earth. The main, most intense phase of its eruption happened roughly 17 to 15 million years ago, which sounds impossibly distant, and yet, in the long memory of the planet, it is recent. It is yesterday afternoon. It is fresh enough that the layers are still clear, still readable, still stacked one on top of another, like the pages of a book that nobody has thought to close. And because it is so young and so well studied, it has become the model, the working example, the thing geologists hold up to the light when they want to understand the far older and far larger eruptions that came before it. We will come back to it. It has more to tell us. But for now, let it sit in your mind as an image, a river of fire crossing a continent, reaching the sea, because here is the strange thing, the thing that pulls at you once you have seen it. This was not a one-time accident. This was not a single bad day in the planet's history. This kind of eruption, the lava pouring not from a mountain but from the ground itself, flooding across whole landscapes, lasting not for hours or for years, but for spans of time that stretch beyond anything a human mind was built to hold. This has happened again and again across the history of the Earth, and tonight, slowly, gently, with no rush at all, we are going to walk into it. We are going to follow the lava down through deep time and see where it leads. There are 3 quiet questions waiting for us in the dark, and I want to lay them out now so you know where we are going, even if you drift off long before we reach the end. The first is simply this: how can lava possibly erupt for 1 million years? The title of this story makes a claim that sounds like a mistake, a thing that cannot be true. Volcanoes erupting for 1 million years without stopping. We will find out what that really means, and the answer is gentler and stranger than you might expect. The second question is this: what does an eruption like that do to the air, to the sky, to the oceans, to the very breath of the world? Because lava is only part of it. The rock is the thing you can see, but there is something invisible that comes with it. And that invisible thing is the part that matters most. And the third question is the oldest argument of all, the one that has divided serious scientists for decades and divides them still. We have all been told that an asteroid killed the dinosaurs. A single object from space, a single terrible afternoon. But at that very moment, on the other side of the world, the ground itself had been bleeding fire for thousands of years. And to this day, the people who study this most carefully cannot agree on which one did the killing, the sky or the ground, or both, working together. We will sit with that question. We will not pretend it is solved, because it is not. But we will hold it up and turn it over slowly and see all of its faces. So that is the journey, how lava can pour for 1 million years, what it does to the air, and whether, at the end of the age of the dinosaurs, it was the sky or the ground that closed the book. 3 questions and a long, calm walk through deep time to answer them. Before we go down into it, let me ask you something, just quietly, in passing. I am always curious where in the world this story is reaching you tonight. Whether you are in a city or out somewhere with the dark, pressing close against the windows, whether it is winter where you are or the middle of summer, whether you are far north or near the sea. If you feel like it, tell me down in the comments. Where in the world are you listening from tonight? I do read them, and if you have wandered in here for the first time and you find that this slow kind of story suits you, that being walked gently through something vast and old is the thing that lets your shoulders come down and your eyes grow heavy, then you might think about subscribing so the next one finds you when you need it, but there is no hurry about any of it. None of this is going anywhere. The lava has been waiting for millions of years. It can wait while you settle. So settle. Let your weight sink into wherever you are lying. Loosen your jaw. Let the day you have just had begin to drift a little distance from you, the way a boat drifts from a dock when you finally let go of the rope. We are going to go a long way back and a long way down, and there is nothing you need to do but follow the sound of my voice as it carries you there. Let us leave the Pacific Northwest for now and travel halfway around the world and far, far further back in time. 66 million years ago, give or take, on the western side of what is now India, the ground was open and the lava was rising, and it had been rising in one form or another for an almost unimaginable stretch of time. This place has a name. It is called the Deccan Traps, and it is one of the largest volcanic features anywhere on the face of the Earth. Let me give you the scale of it slowly, because scale is the whole point, and it is the kind of thing the mind can only take in one piece at a time. Today, after 66 million years of wind and water and weather wearing it down, grinding at its edges, carrying it away grain by grain, the Deccan Traps still cover roughly 500,000 square kilometers of west-central India. 500,000. That is what is left after 66 million years of erosion. The original extent before all that wearing away is estimated to have been something closer to 1.5 million square kilometers. 1.5 million. An area you could lay across whole nations and still have lava to spare. And it is not just the spread of it across the land, it is the depth. In places, the pile of lava is over 2,000 meters thick, 2 kilometers of stone stacked straight up. And it is not one solid block, not one single enormous outpouring that hardened all at once. It is built from dozens upon dozens of individual flows, each one laid down separately, each one cooling and hardening before the next came over the top of it, layer upon layer upon layer, like sediment, like the rings of an ancient tree, except that each ring is a sheet of molten rock, the thickness of a building. You can stand at the base of one of these piles and look up, and you are looking at time. Every layer is an eruption. Every band of dark stone is a moment when the ground opened and poured, and then a long quiet, and then it poured again. When you add it all up, the total volume of lava that came out of the Deccan Traps is estimated at over 1 million cubic kilometers, possibly as much as 1.33 million. And a number like that means almost nothing on its own, the way very large numbers tend to slide off the mind without leaving a mark. So let me give you something to hold on to. Imagine the entire continental United States. All of it, from the Atlantic to the Pacific, from the Canadian border down to Mexico, every city, every mountain range, every plain and forest and desert. Now imagine pouring molten rock across the whole of it, evenly, until the entire country lay buried beneath a layer of basalt several hundred meters deep. That is roughly how much lava came out of the Deccan Traps. Enough to drown a continent. And it did not arrive all at once in a single afternoon of horror. It came in pulses over an enormous span of time, building that buried continent's worth of stone slowly, patiently, the way a tide builds a beach grain by grain. Except the grains here were sheets of fire the size of countries. There is a small detail in the name of this place that I find quietly satisfying, the kind of thing that turns out to be truer and stranger than you would guess. And it is worth pausing on because it tells you something about how this lava actually looks. The word is trap. The Deccan Traps, the Siberian Traps, which we will meet later. The word trap in this context has nothing to do with a snare, nothing to do with catching anything. It comes from an old Swedish word, trappa, which means a stair or a step, a staircase. And once you know that, you can never unsee it, because that is exactly what this landscape looks like. When you erode a thick pile of stacked lava flows, when the wind and the rain get to work on dozens of layers of basalt that are each a little harder or a little softer than the one above and below, what you carve out is not a smooth slope. It is a series of steps, great flat terraces one above the other, marching up the hillside like a staircase built for something far larger than a person. The Deccan Plateau is shaped this way. The cliffs of the Columbia River basalts are shaped this way. Stair after stair after stair, each one a frozen flood. The people who first described this kind of country saw the steps and reached for the word for steps and the word stuck. And now when a geologist says trap basalt, they are really saying stair basalt, lava that erodes into stairs. So picture it now gently as you lie there. A vast plateau in west-central India. Dark stone, weathered and old, stepping upward in great flat terraces under a wide sky. And beneath your feet, 2 kilometers down in places, dozens of separate floods of lava stacked one on top of another, each one a record of a day or a season or a year when the ground opened and the fire came out and spread itself across the land. 500,000 square kilometers of it today, 1.5 million once, over 1 million cubic kilometers of stone, enough to bury a continent, a staircase of fire 66 million years old, sitting quietly in the sun. And here is where it begins to matter, where the lava stops being only a marvel of scale and starts to become part of a much larger and much more uncertain story. Because that number, 66 million years, is not a number geologists chose at random, and it is not a round number reached for the sake of tidiness. It is a number they have worked very hard to pin down with great care, using methods that read the slow ticking of atoms inside the rock itself. And it is a number that should make you sit up a little, even as you are drifting off, because 66 million years ago is a moment with another name. It is the moment the dinosaurs died. It is the moment, or very nearly the moment, when the great age of the giant reptiles ended, when 3/4 of all the species on Earth vanished from the record, when the world changed so completely and so suddenly that geologists draw a line right through the rock and give the time before it one name and the time after it another. That line has a name too, and we will come to know it well tonight. They call it the Cretaceous-Paleogene boundary. The Cretaceous, the last great age of the dinosaurs, on the one side; the Paleogene, the age that came after, the age that belonged to the mammals, and eventually far down the line to us, on the other side. And the line between them, the boundary, is one of the most studied stripes of rock anywhere on the planet, because something happened there. Something enormous, something that ended a world. And the strange, uncomfortable, fascinating fact at the center of this whole story is that the Deccan Traps were erupting at exactly that moment. Not near it, not roughly around it, at it. The most intense phase of all, that lava, all that buried continents worth of fire, came down right across that same boundary, right at the same 66 million year mark when the dinosaurs disappeared. The ground in India was pouring fire at the very instant the world was ending. Now you might already know the other half of this story, the famous half, the half that made it into every book and every film. You might be thinking, but it was an asteroid. Everyone knows it was an asteroid, a great rock from space, falling out of the sky, striking the Earth and throwing up a darkness that smothered the world. And you would not be wrong, that asteroid is real. The crater it left is real, and we will stand at its edge before the night is through. But you can perhaps already feel the shape of the problem, the thing that has kept serious people arguing in serious journals for decades now. Two enormous catastrophes, two world-ending events, both happening at the same moment in Earth's history, on opposite sides of the planet, a rock from the sky and a sea of fire from the ground. Both of them more than capable, on their own, of doing terrible damage to the living world. Both of them landing at the same instant in the rock record. So which one did it? Which one killed the dinosaurs? The sky or the ground? That is the question we are going to carry with us through the whole of this long night, and I want to be honest with you about it right from the start, because there is nothing worse than being promised an answer that does not exist. I am not going to tell you it was settled. I am not going to pretend that the scientists have all agreed and gone home. They have not. This is genuinely one of the great unresolved debates in the study of the deep past. There are careful, brilliant people who have spent their whole lives on this question, who believe the asteroid did nearly all of the killing and the volcanoes were a side note. And there are other careful, brilliant people, just as serious, just as well-armed with evidence, who believe the volcanoes had already brought the living world to its knees long before the asteroid ever arrived, and that the rock from the sky simply delivered the final blow to a world that was already dying. And there are still others who suspect the two were connected, that the impact and the eruptions were not strangers passing in the night, but were somehow part of the same catastrophe. We will lay all of that out slowly when the time is right. We will look at how they pinned the date of the lava in the first place, using the patient methods that let a person read the age of a stone. We will stand at the edge of the crater the asteroid left, and we will sit with the genuine, unresolved tension of it, and we will not force a verdict because the rock has not given us one. There is a particular kind of peace, I think, in being allowed to rest inside an open question. So much of our waking life is spent demanding answers, needing to know, needing things resolved before we can set them down. But the deep past does not work that way. The deep past offers us mysteries that may never close, and asks only that we look at them with care and with wonder. And tonight, that is all we have to do. But before we follow the dinosaurs down into the dark, before we stand at the boundary and weigh the sky against the ground, We need to understand the fire itself. We need to understand how it is even possible for lava to erupt the way the title promises, for 1,000,000 years, because that phrase, 1,000,000 years without stopping, sounds like a thing that simply cannot be true. Nothing erupts for 1,000,000 years. No fountain of fire could burn that long. And you are right to be suspicious of it. The truth is gentler and slower and far more interesting than a 1,000,000-year fountain, and understanding it is the key that unlocks the rest. So let us go back to the lava, back to those stacked layers 2 kilometers thick, back to the dozens of separate flows, and let us ask, very slowly, in the quiet, what does it actually mean for the ground to burn for 1,000,000 years? Let us start, as the geologists do, with a single flow. Not the whole 1,000,000 years at once, because the whole is too large to hold in the mind, especially a mind that is loosening its grip on the day. Just one flow, one pouring of the earth. Roughly 17 to 15 million years ago, in what we now call the Pacific Northwest of North America, the ground in eastern Washington and Idaho opened, not as a single cone, not as a mountain with a smoking peak, the way you might picture a volcano. It opened along long cracks, fissures in the crust, and out of those cracks came basalt, molten rock, dark and fluid, far more fluid than the thick, sticky lava that builds the steep volcanoes of postcards. This was thin and fast and hot, and it did not pile up into a mountain. It ran, and it ran a very long way. A single one of these flows poured out of the ground in eastern Washington or Idaho and traveled west across the land all the way to the Pacific Ocean. Over 500 kilometers. More than 300 miles of molten rock moving across the surface of the continent, and it covered that distance in a matter of days to weeks, while it was still liquid, still glowing, still hot enough to flow. Picture that for a moment, slowly, the way you would picture a dream you are sinking into. A river of fire that does not follow a valley because it is making its own. It crosses the whole width of a region the way a tide comes in across a flat beach. Only it is stone, and it is on fire, and when it finally reaches the sea, it meets the cold water and hisses and hardens and becomes the dark cliffs that are still there today. This is the Columbia River Basalt Group. It is the youngest and the best preserved of all the great flood basalts on Earth, which is a lucky thing for us, because young and well-preserved means we can read it clearly. It covers something like 210,000 square kilometers spread across Washington, Oregon, and Idaho, and it holds a similar number in cubic kilometers of rock, roughly 210,000 of those as well. The layered cliffs you may have seen along the Columbia River Gorge, the stacked dark bands one above another, the strange scoured terrain of the scablands, all of it is carved into this lava. The landscape that was there before, whatever hills and rivers and valleys existed in that corner of the world, was simply buried, drowned in stone. And because it is young, because it is the clearest example we have, geologists used the Columbia River basalts as their working model, the modern key for understanding the much older and much larger eruptions that came before it. If you want to understand the giants, you study the one that is freshest in the rock. But hold on to that single flow for a moment longer, because it is doing something important for us tonight. It is showing us that the Earth can move stone like water across continental distances in a single eruptive breath. And if one flow can do that, then the question that opens beneath us is not really about a single fountain burning for 1,000,000 years. It is about how many of these breaths a planet can take and how far apart, and what they leave behind. There is a triad of unknowns that sits at the heart of all of this, and I want to lay it out plainly, the way you would lay out 3 stones on a table before you and just look at them. The first, how can lava pour for 1,000,000 years at all? The second, what does it do to the air, to the very sky we breathed when the ground bleeds fire on that scale, and the third, the one that has kept careful, serious people arguing for decades. Was it the sky or the ground that killed the dinosaurs? An object falling from space, or the Earth itself opening up? Nobody can give you a settled answer to that last one. Not yet. Perhaps not ever. The scientists who have spent their lives on it are genuinely divided, and that division is not a failure of theirs. It is the honest shape of the evidence. That tension is the spine of everything we will move through tonight. So let me name it once, clearly, and then we can let it hum quietly in the background as we descend. On one side, the falling sky. An asteroid, a great stone from space, striking the Earth at the end of the age of dinosaurs. On the other side, the opening ground, a flood basalt on the far side of the world, larger than almost anything in the rock record, erupting in pulses across that same stretch of deep time. Two candidate killers overlapping in the same narrow window, and the relative weight of each, how much the sky did, how much the ground did, is one of the truly unresolved questions in the earth sciences. We will not solve it. We will hold it. And before we go further into the dark, let me do the small, human thing the night invites. If you are lying somewhere in the world right now, in a bed in one country or another with the lights low and the day finally letting go of you, I would genuinely like to know where you are. Tell me, in the comments, where in the world you are listening from tonight. There is something quietly lovely about 1,000 people in 100 different places, all sinking into the same slow story of fire and stone. And if you are new here, if you have just found this quiet harbor, you are welcome to subscribe so the slow stories keep finding their way to you. That is all. No urgency. We can let it go now and return to the rock. Because there is one other flood basalt we need to meet before we can talk about 1,000,000 years, and it is the one that sits closest to the dinosaurs. It is the one whose name carries the whole mystery in it. It is called the Deccan Traps, and it lies in west-central India on the broad, uplifted land we call the Deccan Plateau. If the Columbia River basalt showed us what a single great flow can do, the Deccan shows us what happens when the Earth does that again and again and again until the rock itself becomes a kind of geography. Today, the Deccan Traps cover roughly 500,000 square kilometers, and I want you to notice that word, today, because it is hiding something. 500,000 square kilometers is what is left after tens of millions of years of rain and rivers and wind have worn it down and carried pieces of it away. Before all that erosion, the original spread of the lava is estimated at something closer to 1.5 million square kilometers. We are looking, in other words, at a ruin, at a third, perhaps, of what once was. And even the ruin is one of the largest volcanic features on the face of the Earth. The volume is the part that strains the mind, so let us take it slowly, with a picture to lean on. The original lava that built the Deccan is estimated at over 1 million cubic kilometers. Some estimates push it toward 1.33 million. 1 million cubic kilometers of molten rock is not a number a person can really feel, so here is the way the geologists make it human. Take that lava and pour it evenly across the entire continental United States, every state from coast to coast, every plain and city and mountain range, and it would bury the whole of it to a depth of several hundred meters, not a coating, not a layer, a burial, an entire continent's worth of land, drowned hundreds of meters deep in dark stone. That is the Deccan, that is what the ground in India once produced. And it did not produce it all at once, in one smooth ocean of lava. It produced it in flows, flow upon flow upon flow, each one pouring out, spreading wide, then cooling and hardening into a flat, dark sheet. And then, After a pause that might last a very long time, another flow pouring out on top of the one before. Stack enough of those together and you do not get a mountain. You get a staircase. In places, the pile of stacked lava in the Deccan is over 2,000 meters thick, 2 kilometers of rock, built entirely from dozens of separate flows, each one a flat step laid on top of the last, climbing slowly into the sky over an unimaginable stretch of time. And here, in that staircase, is where the name comes from, and it is one of those small details that quietly rearranges how you see the thing. We call them traps. The Deccan Traps, the Siberian Traps, and the word trap, in your everyday ear, means a snare, a thing that catches you, something with a hidden danger waiting to spring. It is easy to assume the name was chosen for the menace of it, the deadly lava, the trap that caught the dinosaurs. But that is not it at all. The word has nothing to do with snares. It comes from the Swedish word trappa, which simply means a stair, a step. The early observers looked at these stacked, flat, step-like layers of eroded flood basalt, terraces climbing up the hillsides like the steps of some enormous staircase carved for giants, and they named the rock for its shape. A trap is a stair. Every flood basalt that carries that name carries it for the same reason. The Deccan in India, the Siberian Traps in the far north, both of them named not for what they did to the living, but for the patient, stepped terraces the cooling lava left behind. So when we say the Deccan Traps, we are really saying the Deccan Stairs, and that is a gentler image to carry down into sleep than a snare. A vast staircase of dark stone, 2 kilometers tall in places, built one slow step at a time across the deep past, each step a separate pouring of the earth. We are about to climb down it, step by step, into the question of how those steps were made and how long it truly took, and what was breathing in the air while the ground built them. The timing of the Deccan eruptions is a problem that took most of the 20th century to even approach clearly, and it is worth sitting with how difficult a question it actually is. When we say the Deccan Traps erupted at roughly 66 million years ago, we are not reading a date from a calendar, someone buried in the lava. We are reasoning backward through deep time using the physics of radioactive decay, and the precision of that reasoning has improved enormously over just the last few decades, to the point where we can now say things about 66 million-year-old rock with a confidence that would have seemed fantastical to geologists working even in the 1980s. Two methods in particular have done the sharpest work here. One is called argon-argon dating. The other is uranium lead dating. They sound technical, and the details are genuinely complex, but the underlying idea is one you can hold in your mind without effort. Radioactive elements decay at fixed, known rates. A given atom of potassium will, over time, become an atom of argon. A given atom of uranium will, over time, become an atom of lead. The rate of that transformation does not change with temperature, with pressure, with what happens on the surface above. It simply ticks forward as reliably as anything in nature ticks. So if you take a piece of freshly erupted lava, it starts its clock the moment it cools, and the minerals inside it lock into their crystalline structures. From that point, the ratio of parent atom to daughter atom begins to accumulate, slowly and steadily, in a direction that can be measured. The older the rock, the more daughter atoms you find. And from that ratio, with instruments of extraordinary precision, you can calculate how long ago the clock started, how long ago the lava cooled, how long ago that particular step of the staircase was laid down. When those methods are applied to the Deccan Traps, to basalt samples collected from across the western Deccan Plateau, from the thick lower sections and the thinner upper flows, from the rocks that bear the crystals most amenable to precise measurement, they return again and again to the same approximate answer. The main pulse of Deccan eruption falls at around 66 million years ago. It straddles what geologists call the Cretaceous-Paleogene boundary, abbreviated as the KPG boundary, that razor-thin line in the rock record that marks the end of one great chapter of life and the beginning of another. The Cretaceous was the age of the non-avian dinosaurs. The Paleogene was the age that followed, and the boundary between them is 66 million years old, and the Deccan lavas are tangled around it in time in ways that turn out to matter enormously. But before we come to that tangle, hold the full duration in your mind for a moment, because the 66 million year figure is the center of gravity, the peak of the eruptions, the moment of greatest intensity. The full spread of Deccan activity, the beginning to the end of it, encompasses something on the order of 1 million years, perhaps slightly less, perhaps slightly more. The estimates from the most rigorous recent work tend to fall in that range, several 100,000 years to 1 million or more for the complete eruption sequence. And the title of this video rests on that figure. And the figure is real, but it deserves a moment of honest qualification, because it is easy to hear 1 million years of eruption and picture a single, unbroken river of fire burning continuously through the whole of that time, fountains of lava lighting the sky without pause for a span so long it contains all of recorded human history 10,000 times over. That is not quite what happened, and being honest about the difference matters. Flood basalts do not erupt that way. They erupt in pulses, a period of intense activity, perhaps tens of thousands of years, perhaps more, during which enormous volumes of lava pour out and stack new layers on the ones before. And then a relative quiet. The lava slows or stops. The landscape breathes. Time passes. And then another pulse begins, another pouring, another step added to the staircase. The 1 million years is the cumulative span of the whole sequence, from the first pulse to the last. The total volume of lava produced over that span is the million cubic kilometer figure, the enough to bury the United States number. But no single living creature would have watched 1 million years of continuous eruption. The pulses came and went over that span, the way a river rises and falls across a long, slow century of rain. A human lifetime, dropped anywhere into the Deccan eruption sequence, might witness only the dark quiet of the intervals, a vast plateau of cooling black rock, the faint shimmer of distant heat, the landscape simply there, still and geological and ancient seeming even then. And yet the cumulative weight of those pulses laid end to end across the deep past produced something genuinely staggering. A pile of solidified lava more than 2 kilometers tall in places, a landscape of stepped dark stone covering an area that was, before erosion reduced it, on the order of 1.5 million square kilometers, larger than all of Western Europe, and all of it from the first cautious pour to the last, woven around a single, terrible, 66 million-year-old moment in Earth's history. That moment is the Cretaceous-Paleogene boundary. And to understand what makes the Deccan debate so alive, so unresolved, so genuinely compelling to scientists who have spent entire careers in this question, you need to know what else happened at that boundary. Because the Deccan was not the only thing. Beneath the Gulf of Mexico, buried under kilometers of sediment and younger rock beneath the Yucatan Peninsula, on the coast of what is now Mexico, there is a crater. You cannot see it from the surface. It does not announce itself with a dramatic depression in the landscape the way you might expect from the most consequential impact in the last several 100 million years of Earth's history. It is hidden, ghostly, detectable only through the patient work of gravity surveys and drill cores and the subtle signatures that buried structure leaves in rock. But it is unquestionably there, and its dimensions are extraordinary. It is roughly 180 kilometers wide. Its center lies just offshore in shallow water, and its edges loop across the peninsula in a shape that can be traced even through all the burial, all the erosion, all the millions of years of geology that have overprinted it. The asteroid or comet that made it, or the bolide, to use the precise term, was somewhere between 10 and 15 kilometers across. About the size of a moderate mountain range moving at tens of kilometers per second when it hit. The impact is dated to essentially the exact KPG boundary, not approximately, not within a few million years. To the boundary itself at 66 million years ago within the precision of the methods available to measure it. This crater is named Chicxulub after a small town near its center. And it was the Chicxulub event that entered popular culture as the thing that killed the dinosaurs, the bad day, the rock from the sky that ended an age. That story is not wrong. The impact was real. The devastation it caused was real. The coincidence of its timing with the mass extinction is not a coincidence at all, but a causal relationship that essentially no serious scientist disputes. But here is where the ground becomes complicated, and where the sleep-soft darkness of this story opens into something genuinely unsettled, because the Deccan Traps were also there. At 66 million years ago on the other side of the planet from the Yucatan, the Deccan eruptions were in progress. The asteroid hit a world that was already, in some substantial sense, under volcanic stress. And the question, the real, live, professionally contested question, is what that means for how the extinction actually happened. There are three main models that serious researchers have argued for, and none of them has won. Understanding all three and understanding why none has won is the closest thing to a satisfying answer that the evidence currently permits. The first model is sometimes called impact dominant. In this view, the asteroid did nearly all the killing. The Chicxulub impact was so catastrophic seen in the immediate blast, the global firestorm, the vast cloud of debris that darkened the sky for months or years, the cooling and the collapse of photosynthesis, that the biosphere would have collapsed essentially regardless of what the Deccan Traps were doing. The Deccan eruptions are acknowledged as real and as large, but in this model they are secondary, a geological coincidence that happened to overlap in time with the far more acute crisis of the impact. The dinosaurs were not weakened by volcanism and then finished by a rock. They were struck by a rock of such force that nothing could have survived it. The second model is sometimes called volcanism primed, or the double whammy hypothesis, and it runs the causation in a different direction. In this view, the Deccan eruptions had been going on for some time before the asteroid arrived, pumping carbon dioxide and sulfur into the atmosphere in pulses, causing climate swings that shifted temperatures up and down on timescales too rapid for ecosystems to absorb gracefully. Sea levels changed, ocean chemistry shifted. The carbonic acid produced when CO2 dissolves in seawater had been slowly lowering the pH of the oceans, making conditions harder for the creatures, corals, mollusks, tiny planktonic organisms whose shells and bodies are built from calcium carbonate that dissolves in acid. The biosphere in this model was not at its peak health when the asteroid arrived. It had been stressed, perhaps for tens of thousands of years, by the slow volcanic poisoning of the Deccan. And the asteroid, enormously destructive on its own terms, delivered the final blow to a world already weakened, already bending under a different kind of pressure. The third model is the strangest and in some ways the most intellectually beautiful of the three. It is called, roughly, impact-triggered volcanism, and it begins with a question that takes a moment to absorb. What if the asteroid impact itself changed how the Deccan Traps erupted? This model is based on the observation that a bolide impact of the Chicxulub scale sends seismic energy, enormous, planet-spanning waves of compression and shaking, rippling through the entire Earth. And some researchers have proposed that those waves, when they reached the far side of the world where the Deccan plumbing was already primed and ready, may have disturbed the volcanic system, perhaps opening new conduits, perhaps accelerating eruptions that were already in progress. In this model, the impact and the volcanism are not independent coincidences, they are mechanically linked. The sky event triggers the ground event. The rock from space and the fire from the Earth are, in some sense, the same catastrophe, one detonating the other. All three of these models have peer-reviewed support in the scientific literature. All three have been argued by serious researchers with real data, and all three, as of the time when this is being written, remain in genuine contention. There is no consensus. There is no settled answer. There is, instead, one of the most vigorous debates in all of paleontology and geology, a debate that turns on the question of timing, specifically on the question of when exactly the main pulse of Deccan eruption occurred relative to the moment of the Chicxulub impact. And it is here, in the attempt to pin that timing down, that the story offers something almost theatrically perfect as an illustration of how science actually works at its sharpest and most contested edge. In 2019, two independent research teams published competing chronologies of the Deccan eruptions in the same issue of the journal Science. The same issue. Side by side in the same pages, two groups of researchers using the same general class of radiometric dating methods applied to overlapping but not identical sets of Deccan samples arrived at conclusions that pointed in different directions. One team, led by researchers at the University of California, Berkeley, the names most associated with this work are Paul Renne and Courtney Sprain, argued that the bulk of the Deccan lava erupted after the Chicxulub impact. In their chronology, the main volume of eruption came in the period following the boundary, not before it. If they are right, the Deccan was not the primer. It was, if anything, a factor in the aftermath, shaping the long, slow recovery of life following the impact event, but not the cause of the initial collapse. The other team, led by Blair Schoene at Princeton University, used uranium lead dating on zircon crystals within the Deccan flows and argued for a different picture, one in which a major pulse of Deccan eruption occurred before the boundary, before the impact. In Schoene's chronology, there was substantial volcanic activity in the period leading up to the KPG event, meaning the biosphere was already under volcanic stress when the asteroid arrived. Two teams, two careful studies, two opposing answers, published in the same issue of one of the most prestigious scientific journals on Earth. It would be tempting to read this as a failure, as evidence that the science is confused or unreliable, but it is in fact the opposite. It is evidence that the question is genuinely difficult, that the tools being brought to bear on it are precise enough to find real disagreements in the data, and that the scientific community is being scrupulously honest about a problem it has not yet solved. The uncertainty is not a crack in the method. The uncertainty is the method working, acknowledging the limits of what 66-million-year-old rock can tell us with confidence. There is no winner to declare here, and any telling of this story that declares one is being dishonest with you. What the evidence supports is this. The Chicxulub impact was real and catastrophic. The Deccan Traps were real and enormous and active around the same time. The precise relationship between them, whether the Deccan primed the killing, whether the impact triggered more Deccan, whether the Deccan mattered at all to the extinction itself or only to the recovery after, remains open. Renne and Sprain say one thing, Schoene says another. The debate continues in journals, at conferences, in the patient work of drilling and sampling and refining the measurements. What we can say with confidence is the outcome. Roughly 75% of all species on Earth disappeared at or near the K-Peak boundary. The non-avian dinosaurs, the ceratopsians and the hadrosaurs and the titanosaur sauropods, and all the others that had walked the Cretaceous Earth for more than 150 million years, were gone. The great marine reptiles were gone. The flying pterosaurs were gone. The ammonites, those coiled shell mollusks whose fossils are found in Cretaceous rock the world over, vanished from a record they had kept for hundreds of millions of years. Something like 3 in 4 species simply ceased to exist, their lineages ending in the rock. It is worth sitting with that number. 75%. Imagine 3 out of every 4 kinds of living things gone. The world that remained was a different world. Smaller, quieter in many places. The niches left vacant by the non-avian dinosaurs would eventually be filled, over millions of years, by the mammals that survived, the small, burrowing, insect-eating creatures that had lived in the shadows of the Cretaceous world and now found themselves in a world without the giants that had defined it for so long. But that recovery was slow, and the loss was enormous, and the debate about what caused it carries the weight of all that extinction behind it. The Deccan Traps sat in the middle of it. Whatever role they played, priming the world, finishing the wounded biosphere after the impact, or doing something in between, they were there. That 2-kilometer thick staircase of dark stone had been building for hundreds of thousands of years before the asteroid arrived, and would continue building for some time after. The planet was pouring itself out in west-central India, while whatever else was happening, happened. And here, in the slow geological dark of that recognition, the question that has been quietly waiting in the background of this whole story begins to press more clearly into view. If the Deccan eruptions were enormous enough to potentially contribute to the greatest biological crisis of the last 100 million years, then the obvious thing to understand is the mechanism. How does pouring lava change the world? What does a flood basalt actually do to the air, to the oceans, to the conditions that life depends on? That is the question the next step of this staircase holds. But before we descend into it, it is worth pausing here, in the specific strangeness of this moment. 66 million years ago, an asteroid and a flood basalt province, both enormous, both destructive, in ways we are still working to understand, happening simultaneously on a planet already ancient, already carrying 4 billion years of its own complicated history. The rock record does not give us a clean answer. It gives us precisely the kind of answer that deep time tends to give, layered, ambiguous, and rich with genuine uncertainty. The Deccan Traps are still there, under the Indian sky, their stepped terraces worn by 66 million years of rain and wind. The Chicxulub crater is still there, invisible beneath its Yucatan blanket of sediment, detectable only by the instruments we bring to it. And between them, in the sediment layers laid down at the K-PG boundary, a thin, global layer of iridium-enriched clay, the fingerprint of the Chicxulub bolide found on 6 continents. The record sits, patient and partial, and not yet fully read. What we carry forward from this moment as we continue deeper into the story of flood basalts and the air they poisoned and the extinctions they helped engineer is not a verdict. It is a question held honestly open. The asteroid and the volcano, the sky and the ground, both credible, both powerful, both present at one of the worst moments in the history of life on this planet. And the scientists who study them, careful and methodical and sometimes in direct disagreement with each other in the same journal issue, still working toward an answer that the evidence has not yet fully yielded. There is something almost peaceful in that if you let yourself feel it. Not the extinction, which was catastrophic and immense and changed the shape of life on Earth permanently, but the question itself. The patient, unresolved question held open across millions of years of rock being worked on by people in laboratories right now, at this moment, as you lie in the dark and let the deep past settle around you. The question is real. The people working on it are real. And the honest uncertainty they carry is not a failure of knowing, but the clearest sign that they are looking at something genuinely difficult and genuinely vast. The Deccan Traps keep their secret at 66 million years, stacked in their dark, patient steppes. The Chicxulub crater keeps its silence under the Yucatan, and the boundary between the Cretaceous and the Paleogene sits in the rock record everywhere on Earth, in chalk cliffs, in roadside outcrops, in cores drilled from the deep sea floor. A thin line marking a world before and a world after, and the ongoing, careful, rigorously honest argument about what crossed that line first. But before we leave that boundary layer, before we move deeper into how these eruptions actually worked and what they actually did to the living world, it is worth pausing on the timing itself, because the timing is not a casual detail, it is the whole argument. The Deccan Traps have been dated by two of the most precise radiometric techniques available to geology. Argon-argon dating, in which the ratio of argon isotopes in a cooled lava tells you how long ago that lava crystallized and sealed its argon inside. And uranium lead dating, which tracks the slow decay of uranium into lead inside certain minerals and gives an independent clock running on a different nuclear mechanism altogether. When two entirely different decay systems measuring different elements converging on the same rock from different angles agree with each other, the result carries a weight that is hard to dismiss. And they agree. The most intense phase of Deccan eruption falls within tens of thousands of years of the Cretaceous-Paleogene boundary, which is itself dated to approximately 66 million years ago. In geological terms, tens of thousands of years is almost nothing. It is a rounding error on a planetary calendar. The cumulative span of Deccan activity, the full duration across which those pulses of lava rose and poured and cooled, and were followed by others, is on the order of 1 million years, perhaps somewhat more, perhaps somewhat less, depending on which measurements you weight most heavily and which margins of error you accept. This is what makes the title honest. The Deccan Traps did erupt across something approaching 1 million years. But here is the correction that honest geology requires, the one that makes the story stranger rather than simpler. 1 million years without stopping, in the rhetorical sense that phrase carries, suggests a single unbroken fountain of lava, one continuous roar of fire and gas, lasting from one geological moment to the next without pause. That is not quite what happened. Flood basalts erupt in pulses, enormous pulses individually capable of burying continents under dozens of meters of molten rock in what geologists would call a geologically brief interval, but pulses nonetheless, separated by quieter periods when the mantle plume beneath had not yet gathered enough pressure or heat to rupture through the crust again. The cumulative total is the 1 million years. Any single human lifetime dropped into that 1 million-year span would have seen only dark, flat, cooling basalt plains stretching to every horizon, with nothing erupting at all, no lava, no ash, just the eerie stillness of a landscape that had been remade and was waiting, patiently, to be remade again. The pulses were separated by intervals that could be thousands of years apart. Long enough for some organisms to recolonize a lava field, long enough for thin soils to form on the cooled rock, long enough that from inside a single human life you would have no way of knowing you were standing in the middle of an ongoing catastrophe that had been unfolding for 500,000 years and would continue for 500,000 more. This is what deep time does. It compresses events that were, from any inhabited perspective, enormously separated into an apparent simultaneity. The Deccan Traps and the Chicxulub impact were, in geological terms, nearly contemporaneous. In human terms, the interval between them may have been tens of thousands of years. Neither of those statements is wrong. They simply operate on different scales of time, and the scale you choose changes the story almost completely. Now, the Chicxulub Crater. It lies buried beneath the Yucatan Peninsula in southern Mexico and beneath the shallow sea floor of the Gulf of Mexico just offshore. It is approximately 180 kilometers wide. The impactor that made it, a single body of rock and possibly ice, a bolide, was estimated at somewhere between 10 and 15 kilometers across, which is to say, roughly the diameter of a city. When it struck the Earth 66 million years ago, it released energy on a scale that staggers any attempt to fully imagine it. The rock of the Yucatan was vaporized and molten and thrown into the upper atmosphere within seconds. A wall of superheated debris spread outward at speeds beyond anything a living organism could outrun. The sky, in the immediate aftermath, would have been on fire in ways that required geological imagination rather than any human analogy. The crater that remains, invisible now beneath layers of later sediment and limestone, is one of the best preserved and best studied impact structures on Earth, and its date is pinned to the KPG boundary with a precision that matches the Deccan radiometric work. They are contemporaneous within the limits of measurement, which is to say, as close together as we can currently tell. And here is where the debate lives, not in whether either of these events happened. Both are established beyond any serious scientific doubt. The Chicxulub impact happened. The Deccan Traps erupted, both at the same geological moment. The debate is about which one bears more of the weight of what followed. Approximately 75% of all species on Earth went extinct at the Cretaceous-Paleogene boundary. The non-avian dinosaurs, which had dominated terrestrial ecosystems for over 150 million years, did not survive it. The ammonites, coiled and elegant in the Cretaceous seas, were gone. Vast numbers of marine species, of plant species, of small creatures whose names most of us have never learned, were gone. The world that came after was recognizably a different world, rebuilt from survivors in lineages that had previously been suppressed or marginal, including the small, warm, fast-breeding mammals from whose descendants you are now descended. Something killed 75% of species. The argument is about what? There are 3 models that have serious peer-reviewed support, and it matters to name them carefully rather than picking one and discarding the others. The first is sometimes called impact dominant. In this reading, the Chicxulub asteroid did the overwhelming majority of the killing through immediate physical catastrophe and through a subsequent decade or more of impact winter, as dust and soot in the upper atmosphere blocked sunlight and collapsed photosynthesis globally. The Deccan Traps were happening in this view, but their contribution was secondary, perhaps even marginal, in the context of an impact event so powerful that it reset the atmospheric and ecological state of the planet in a matter of months. The second model is volcanism primed. Here, the Deccan eruptions had been stressing the global ecosystem for tens of thousands of years before the asteroid arrived, generating volatile swings in climate, pulses of ocean acidification, disruptions to food webs that left the biosphere more vulnerable than it would otherwise have been. In this reading, the asteroid struck a world already weakened, and what might have been a survivable, if brutal, extinction event became unsurvivable. The impact was decisive, but it was decisive partly because the ground had already been prepared. The third model is perhaps the most unexpected, and it involves a feedback between the 2 events, rather than a straightforward competition. Seismic energy from the Chicxulub impact, traveling through the body of the Earth at the speed of sound in rock, may have reached the Deccan hotspot and destabilized it, accelerating or intensifying the eruptions that followed. In this view, the asteroid and the volcano were not merely coincident. The asteroid may have helped trigger a greater outpouring from the Deccan than would have occurred otherwise. The sky fed the ground. All 3 models have evidence behind them. None has been definitively ruled out. And in 2019, the journal Science published 2 papers in the same issue that illustrated, perhaps more vividly than any single moment in recent geological history, just how unresolved this remains. Paul Renne and Courtney Sprain, working at Berkeley, published a chronology that placed the bulk of Deccan lava output after the Chicxulub impact, suggesting that the eruptions intensified following the asteroid, which would fit the impact-triggered model, and also suggesting that the lava was arriving into a world the impact had already devastated, not softening it up beforehand. In that same issue, Blair Schoene and colleagues from Princeton published a different chronology, using uranium lead dating on a different mineral fraction that placed a significant pulse of Deccan eruption before the boundary, before the impact, which is the signature of the volcanism-primed model, ecosystems already stressed when the asteroid arrived. Different laboratories, different radiometric approaches, different conclusions, published simultaneously side by side without either team conceding the field to the other, because neither had sufficient reason to concede. This is not a failure of science, it is science working exactly as it should. The resolution of genuinely difficult questions does not arrive cleanly or quickly, or with everyone in agreement on the first attempt. It arrives through the slow accumulation of measurements, the refinement of techniques, the reanalysis of samples with improved instruments, the gradual convergence of independent lines of evidence towards something that starts to feel like a consensus. That process is underway for the Deccan Chicxulub debate right now in laboratories on several continents, and it has not finished. The rocks are still being read, the numbers are still being refined. What the rocks do agree on without ambiguity is the outcome. Approximately 66 million years ago, the non-avian dinosaurs were gone. 3/4 of species were gone. The boundary is real and it is sharp, at least in geological terms, and it is present in rock exposures all over the Earth, in the chalk cliffs of coastal Europe, in road cuts through the American West, in sediment cores pulled up from the deep ocean floor thousands of kilometers from the nearest shore. Wherever geologists look for it, the boundary is there, a thin dark line or a change in the character of the fossils, a before and an after pressed together in stone. Below the line, the creatures of the Cretaceous. Above it, a world in recovery, emptied and then, slowly, over millions of years, refilled. And so the question becomes, what actually did the killing? Not the question of which candidate, the sky or the ground. Because that question, as we have seen, remains genuinely open, and the rocks have not yet agreed on an answer. But the more precise question of mechanism, of process, of how exactly a vast outpouring of lava from the deep interior of the Earth translates into the death of 3/4 of the species alive on its surface, because lava itself, however abundant, however hot, however relentless in its slow advance, cannot directly reach a pterosaur in the sky or an ammonite coiling through cold Pacific water thousands of kilometers away. The lava is local, the killing is global. Something must carry the harm from the source to the victim, and that something is the air. When basalt pours from a fissure in the crust, not from a cone, not from a crater at a summit, but from a long crack in the ground, sometimes hundreds of kilometers in length, gaping open like a wound in the Earth's skin, it brings with it gases that have been dissolved under enormous pressure in the magma far below. The moment that pressure is released, as the rock rises and pours out onto the surface, the gases escape. They bubble out, they rush upward, they enter the atmosphere in volumes that are difficult to hold in the mind all at once. And among those gases, two matter most for understanding what happens to life on the surface of a planet when a large igneous province is in full eruption. The first is sulfur dioxide. Sulfur dioxide is a colorless gas with a sharp, acrid smell. The smell you might catch near a struck match or near an industrial chimney on a still morning, a smell that catches in the back of the throat and makes the eyes water. In small quantities it is familiar, even unremarkable. But the quantities released by a flood basalt eruption at the scale of the Deccan Traps are not small, And what sulfur dioxide does when it reaches the upper atmosphere in those quantities is something the human body has no equivalent experience for. In the stratosphere, the layer of the atmosphere above the weather, above the clouds, where the air is thin and dry and the sun's light arrives without having been scattered by moisture, sulfur dioxide undergoes a chemical conversion. It reacts with water vapor and oxygen and is transformed into tiny droplets of sulfuric acid sulfate aerosols suspended in the stratosphere in a haze so fine and so high that rain cannot wash it out. These aerosols are extraordinarily efficient at reflecting sunlight. They act, in effect, as a kind of planetary mirror, angled back towards space, and the result is that less of the sun's energy reaches the surface of the Earth. The surface cools. Not slowly, in the manner of the gradual cooling that attends the long cycles of ice ages which unfold over tens of thousands of years, at a pace that even a species as slow-breeding as an elephant can adapt to across many generations. This cooling is faster, measured not in tens of thousands of years, but in years, or in decades, in the lifetimes of individual organisms. A volcanic winter. The sky becomes permanently hazed at the edges, the sunlight thinner and more diffuse, the seasons shorter in their warmth, the average temperature across the planet nudged downward by degrees that matter enormously to organisms calibrated over millions of years of evolution to exist within a narrow band of conditions. And the same gas that makes the sky reflective also returns to the surface, not as sulfur dioxide but as sulfuric acid dissolved in rainwater. Acid rain. Not the mildly acidic rain that falls in regions downwind of industrial areas today, but rain significantly more corrosive than that, falling across broad regions, soaking into soils, running into rivers and lakes, washing into the shallow margins of the sea. The soils become more acidic, the rivers become more acidic. The plants that root in those soils, the insects and amphibians and small creatures that depend on those rivers, the reefs and estuaries at the ocean's edge, where so much marine life concentrates, all of them experience the chemistry of their world shifting in ways that their physiology may or may not be able to tolerate. This is the first blow, the sharp one, the cooling and the acid, and it arrives relatively quickly because sulfur dioxide, once injected into the stratosphere in sufficient quantity, produces its effects within months to years. It is the fast-acting agent in the flood basalt's arsenal, but the second gas is slower and in some ways more profound, and it is the one that makes the situation so much worse than a simple cooling event. Carbon dioxide. Carbon dioxide is also released in enormous quantities by flood basalt eruptions. It is, in fact, released in even greater absolute quantities than sulfur dioxide because basaltic magma holds a great deal of it. And carbon dioxide, unlike sulfur dioxide, does not produce aerosols in the stratosphere. It does not reflect sunlight. It does not cool the planet. Instead, it does the opposite. It is a greenhouse gas, and it accumulates in the atmosphere over time, trapping heat that would otherwise radiate back into space, and it does so persistently, because carbon dioxide, once added to the atmosphere, is not quickly removed. It does not wash out with the rain in the way that sulfur dioxide does. It remains for thousands of years, gradually drawn down only by the slow weathering of rocks and the uptake of plants and the absorption of the ocean. Over the long term, over the span of tens of thousands to hundreds of thousands of years, the carbon dioxide released by a large igneous province accumulates and warms the planet, and the ocean absorbs a great deal of that carbon dioxide. When carbon dioxide dissolves in seawater, it forms carbonic acid. The ocean becomes more acidic, not dramatically, not in a way you could taste if you drank it, but measurably chemically in ways that matter enormously to a vast range of marine organisms. Many of the creatures of the Cretaceous Sea, ammonites, belemnites, certain plankton, reef-building organisms, built their shells and their skeletons from calcium carbonate. And calcium carbonate is soluble in acid. As the ocean's chemistry shifted, the process of building and maintaining those shells became more difficult, more energetically costly, eventually impossible in the most acidified conditions. The shells of marine creatures, which had been stable features of ocean chemistry for hundreds of millions of years, began to dissolve. So the biosphere at the end of the Cretaceous was being struck from two directions simultaneously. From the sulfur, short, sharp pulses of cooling, acid rain soaking into soils and river systems, the sun dimmed behind a stratospheric haze. From the carbon dioxide, a slow, persistent warming building over thousands of years, the ocean growing more acidic, the chemistry of the sea shifting away from the conditions that the organisms living in it had evolved to inhabit. And these two forces did not arrive in sequence, they overlapped. The sulfur cooling would pulse, then ease as the aerosols gradually settled out of the stratosphere and the sky cleared a little. Then the next major eruptive pulse would inject another wave of sulfur, and the cooling would deepen again. All the while, the carbon dioxide from every previous pulse continued to accumulate, pushing the background temperature slowly upward. The biosphere was being whipsawed, cold, then warmer, then cold again, but never returning to where it had started because the baseline was shifting. An organism that survived one cold pulse might find itself trying to adapt to a warmer, more acidic ocean in the interval between pulses, only to be hit by the next cooling when conditions had barely begun to stabilize. The ecosystems that had taken hundreds of millions of years to assemble could not adapt to conditions that changed faster than evolution operates. This is the mechanism that makes a flood basalt a mass extinction event, not the lava, not the heat of the rock itself, the gases, the whipsaw of the gases acting on different time scales, pushing the planet's climate back and forth across thresholds that life could not cross quickly enough. And there is one more chemical signal worth pausing over because it appears in the rock record in a way that allows geologists to read the fingerprint of these eruptions even in places where no lava flowed, even in sediments deposited in the middle of an ocean thousands of kilometers from any erupting fissure. Mercury. Mercury is released by volcanic activity in trace quantities, small amounts dispersed into the atmosphere, along with the sulfur and carbon dioxide and dozens of other gases. Under normal geological conditions, the background level of mercury in the atmosphere is very low, and the amount of mercury that settles into marine sediments accumulating on the seafloor is correspondingly very low. It becomes part of the chemical signature of the rock, present but barely. When geologists core through ancient marine sediments and measure the concentration of mercury in the layers, what they usually find is a consistent, low background level punctuated by occasional small variations. But at the boundaries of mass extinctions, at the layers that correspond to the moments when large igneous provinces were actively erupting, the mercury concentration spikes sharply. The signal is distinctive, and it has now been found at multiple extinction horizons in sediments from multiple locations around the world, in rock that was deposited far from any eruptive center. The mercury rode the atmosphere from the volcanic source to the distant ocean, settled into the sediment, and stayed there. Preserved, readable hundreds of millions of years later by a geologist with the right instruments. This mercury anomaly is one of the strongest chemical arguments for linking the Deccan Traps to the events at the Cretaceous-Paleogene boundary and for linking other large igneous provinces to the other extinctions with which they coincide in time. It is a fingerprint left in the rock by the act of eruption itself, independent of the debates about timing and relative contribution, independent of whether any particular flow occurred before or after the boundary. The mercury was in the atmosphere. The mercury settled into the sediment. The mercury is still there. It is a kind of geological testimony. Quiet, patient, not given to exaggeration or interpretation, simply present in the stone at the moment when the world changed. and the world has changed in this way more than once. The Deccan Traps are not unique. They are one instance of a process that the Earth has returned to repeatedly across its history, a process that geologists now recognize as a distinct category of geological phenomenon with its own name, the Large Igneous Province. A large igneous province, a lip, is exactly what it sounds like. An enormous accumulation of igneous rock, whether erupted onto the land as a continental flood basalt or onto the seafloor as an oceanic plateau, emplaced in a geologically short period of time, typically driven by a rising column of anomalously hot rock from deep in the mantle. A mantle plume, a buoyant upwelling in the slow plastic flow of the Earth's interior, carrying heat from depths that we can barely reach even in theory, rising over millions of years until it reaches the base of the crust and spreads out like a drop of food dye in still water, heating the rock above it, driving it to melt, feeding magma upward through fissures and cracks to pour out onto the surface. The Deccan Traps formed over a mantle plume. The same plume, or what remains of it, is today expressed as the volcanic activity of the Reunion hotspot, a small island of volcanic rock in the Indian Ocean, a tiny current remnant of the engine that once flooded west-central India with over 1 million cubic kilometers of basalt. And 4 of the 5 great mass extinctions in the history of complex animal life on Earth coincide with the formation of a large igneous province. 4 of 5. This is not a coincidence that scientists regard lightly. It is one of the most striking patterns in the geological record, and understanding why that pattern exists, what it is about a rising mantle plume and the basalt it produces that is so reliably lethal to life, is what the mechanism of the sulfur and the carbon dioxide and the mercury is trying to explain. The oldest of those 4, and by a significant measure the worst, is not the one that killed the dinosaurs. The worst extinction in the history of animal life on Earth happened roughly 252 million years ago, at the boundary between the Permian period and the Triassic period. It is called, with an economy that carries real weight, the Great Dying. In the Great Dying, approximately 90% of marine species ceased to exist, not declined, not reduced in range, not stressed to the edge, ceased. 90%. The ocean, which had supported a staggering diversity of life for hundreds of millions of years, corals and brachiopods and trilobites and crinoids, and the vast variety of fish and invertebrates that had come and gone and evolved across the Paleozoic era, was emptied of almost all of it. The land fared somewhat better, but not much. Something on the order of 70% of terrestrial vertebrate species are estimated to have been lost. The biosphere that emerged from the Permian had been among the richest in Earth's history. The biosphere that limped out on the other side of the boundary was a remnant, a skeleton. The Great Dying was caused, in the dominant scientific understanding, by the eruption of what we now call the Siberian Traps. The Siberian Traps were, in their original volume and extent, even larger than the Deccan. They cover an enormous area of what is now Siberia, a part of the world so remote and so poorly exposed along most of its length that the full scale of the province took many decades of geological mapping to establish. But the Siberian Traps, in addition to being large, had a characteristic that may have made their environmental impact particularly catastrophic. They erupted through what was already there. The crust of Siberia at the time of the Permian-Triassic boundary was not simple, clean basalt all the way down. Beneath the region lay thick deposits of coal, the accumulated plant material of Carboniferous and earlier swamp forests, compressed and altered by time and pressure into organic-rich rock, and thick beds of salt and other evaporates, minerals deposited by the evaporation of ancient seas. As the magma rose through these deposits, it cooked them. It heated the coal, driving off vast quantities of additional carbon dioxide and methane, supercharging the greenhouse effect far beyond what the basalt alone would have produced. It heated the salt and the evaporates, releasing chlorine and other halogens into the atmosphere, chemicals that attack the ozone layer and that, in sufficient concentration, are directly toxic to biological tissue. The Siberian traps did not just pour basalt onto a clean surface and release the gases contained in the magma. They also incinerated underground hundreds of meters of fossil fuel, sending that additional carbon into an atmosphere already under severe chemical stress. And they added a layer of chemical toxicity, the halogens, on top of the greenhouse warming and the sulfur cooling and the ocean acidification that the flood basalt mechanism would have produced by itself. The result was an extinction so severe that the Cretaceous-Paleogene event, the one that ended the dinosaurs, the one we find most dramatic because the creatures lost were large and spectacular, and because an asteroid from space was involved, looks, in terms of raw biological loss, like a smaller catastrophe by comparison. The Great Dying remains the benchmark, the worst thing that has happened to life on this planet as far as the fossil record allows us to determine in all the hundreds of millions of years since complex animals first appeared in the sea. And it was done by lava, by a mantle plume rising through the crust of Siberia and pouring its heat and its gases over millions of years of volcanic pulses into an atmosphere and an ocean that could not absorb the disruption. The Earth recovered. It always has recovered given enough time, not back to what it was, because what it was no longer existed, but forward into something new. The Triassic that followed the Great Dying was a world in which the survivors, the organisms that had, by chance or by physiological flexibility or by sheer luck of living somewhere that was slightly less affected, made it through, began the long process of filling the vacated ecological space. It took millions of years. The diversity that had been present in the Permian Ocean was not restored in the Triassic, not fully, not for a very long time. And then, roughly 50 million years after the Great Dying, the Earth erupted again. 201 million years ago, at the boundary between the Triassic and the Jurassic periods, another large igneous province came into being. This one is called the Central Atlantic Magmatic Province, the CAMP, and it is, in geological terms, one of the most remarkable volcanic events in the record, not because of its absolute size, though it was immense, but because of its geography. When the Central Atlantic Magmatic Province erupted, the continents of the world were arranged very differently than they are today. The supercontinent of Pangaea, the vast single landmass that had gathered most of the Earth's continental crust together through hundreds of millions of years of plate motion, was beginning to pull apart. A rift was forming, a crack, running roughly north to south through what is now the middle of the Atlantic Ocean basin, and along and around that rift, as the crust began to stretch and thin and fracture, magma rose and flooded outward. The lava poured onto the surface of a continent that was in the process of tearing itself in two, and because it erupted during a continental rifting event, the basalts of the Central Atlantic Magmatic Province were distributed across a landmass that subsequently moved apart. Today, the remnants of those eruptions, eroded, buried under younger sediments in many places, but still identifiable by their composition and their age, are found on 4 separate continents. In eastern North America, in the ridge and valley country of the eastern United States and Canada, in South America, in the northeastern coastal regions of Brazil, in West Africa, in Moroccan and other coastal outcrops, in southwestern Europe, in fragments preserved beneath younger rock in Iberia and elsewhere. 4 continents, one eruption now separated by the ocean that opened in the space left behind when the continents drifted apart. The Atlantic Ocean, which today stretches thousands of kilometers between the shores of the Americas and the shores of Africa and Europe, was born in the violence of this rifting, and the Central Atlantic magmatic province was, in a real sense, both the herald and the engine of that birth. The eruptions weakened the crust tore, the ocean began to form. And at the Triassic-Jurassic boundary, somewhere between perhaps 50 and 80% of species on Earth were lost. A mass extinction now understood to be closely associated in time with the camp eruptions, driven by the same mechanism of sulfur cooling and carbon dioxide warming that the Deccan Traps deployed in slower and less concentrated form at the end of the Cretaceous. The end Triassic extinction cleared the way, among other things, for the ascent of the dinosaurs. The dinosaurs had existed through the Triassic, but they had been minor players in a world dominated by other groups of archosaurs, by large therapsids, by a diverse range of creatures that had adapted to the post-Great Dying world in their own ways. When the camp eruptions killed those other groups, the ecological space they had occupied became available. The dinosaurs, more physiologically flexible or simply more fortunate in their geographic distribution relative to the worst effects, survived in larger numbers and diversified into the vacated niches. The age of dinosaurs was made possible in part by a large igneous province, and the age of dinosaurs was ended in part, or perhaps entirely, by another one. There is something in this pattern, and the flood basalt erupts, the world empties, the survivors diversify into new ecological possibilities, the world refills, and then tens of millions of years later, another plume rises and the cycle begins again. That is not comfortable in the way that comfortable things usually are, but that carries its own kind of long perspective. The Earth's history, read through the record of these eruptions and extinctions and recoveries, is not a story of steady progress or of increasing safety. It is a story of periodic, catastrophic disruption and patient, slow renewal. The baseline is always changing. What was abundant becomes rare or absent. What was rare or absent becomes abundant. The process is indifferent to any particular species or any particular ecosystem, and it operates on timescales that dwarf even the longest span of human civilization by factors of thousands. To hold that in the mind, lying quietly in the dark, is to feel something shift in the sense of scale. The troubles of the day, whatever remained of the day when you lay down, exist on a timeline so brief, so narrow, so vanishingly thin compared to these deep time rhythms that they take on a different quality when held next to them. Not that they don't matter. They matter in the way that everything that happens in a life matters to the person living it. But they are small, they are momentary. And the Earth has been through worse. The Earth has been through the worst several times over, and it is still here. And the air above you is still breathable, and the dark is quiet. The mercury in the sediment remembers. The stair-stepped lava of the Deccan remembers. The four-continent scatter of the camp basalts remembers. The coal beneath Siberia remembers what it was like when it burned. And the rocks are patient. They will wait for the instruments to improve and the measurements to be made again with better precision, and they will tell us, in the end, as much as they are able to tell. There is a point worth pausing over before moving from the terrestrial story, the story of flood basalts on land reshaping the air above the continents, to the equally vast and perhaps even more difficult to imagine story of what happens when a mantle plume rises not beneath a continent but beneath the floor of the deep ocean. And that point concerns the word enormous, which has appeared many times in the preceding passages and which risks becoming a kind of comfortable placeholder, a word used to gesture at scale without actually conveying it. So consider for a moment the volume of the Deccan Traps, more than 1 million cubic kilometers of basalt. In places, the stack of lava flows is more than 2,000 meters thick, taller than the highest peaks of many of the mountain ranges in Europe, taller than the full vertical relief of many landscapes that seem, to human eyes, impressively rugged. And that thickness is not the result of a single event. It is the accumulated product of dozens of individual flows, each one perhaps tens of meters thick, poured out one atop the next over the course of the eruption's long history. Each individual flow would have been in human terms an incomprehensibly destructive event, a sheet of lava moving slowly but irresistibly across an area of land that might have taken days or weeks to cross on foot, burying the landscape beneath it, eventually cooling to rock and becoming the foundation on which the next flow would be deposited. But between those individual flows there were intervals, time for the surface to cool, time sometimes for thin soils to form on the hardened lava, for plants to establish themselves on the new surface, for small creatures to return and begin the process of inhabiting the landscape again. And then the next pulse would come, and the landscape would be buried again. And then another interval, and then another pulse. This is what the rock record inside the Deccan tells us, not a single continuous outpouring, but a sequence of events, each enormous by any human standard, separated by pauses of varying length, adding up over the course of hundreds of thousands to perhaps 1,000,000 years to the total volume that eventually solidified into the stepped plateau of west-central India. This pulsed character of flood basalt eruptions is what allows them to be so environmentally destructive over such a long span of time. A single massive eruption, however large, would inject its gases into the atmosphere and then stop. The atmosphere would gradually recover, the climate would gradually restabilize, the ocean chemistry would slowly return toward equilibrium. Life would be stressed, perhaps severely, but the damage would be finite and the recovery would have space to begin. But a series of pulses, each one injecting another surge of sulfur dioxide and carbon dioxide into an atmosphere that has not fully recovered from the last surge, compounds the damage. The whipsaw continues. The intervals of relative calm are not calm enough or long enough to allow full recovery before the next pulse arrives. The biosphere is kept continuously off balance, unable to stabilize, unable to adapt to any single set of conditions because the conditions keep shifting. This is the particular cruelty, if geological processes can be said to have such a thing, of the flood basalt as an extinction driver. Not its instantaneous power, which is less than the Chicxulub impactor on any single day, but its persistence, its cumulative effect, built up across thousands of pulses over hundreds of thousands of years, hitting a biosphere that is already weakened and cannot rest. The mercury spikes in the sediment record this persistence. At some extinction boundaries, the mercury anomaly is not a single peak, but a series of peaks spread across the thickness of rock that corresponds to the duration of the eruption. Each peak is a pulse. Each pulse is a wave of sulfur and carbon riding through the atmosphere and settling into the sediment of a distant sea. The record of the eruption is written in trace metal chemistry across thousands of kilometers and hundreds of thousands of years of sediment. It is a strange kind of archive, not a library or a cave painting or a written document, but a chemical signal distributed through stone, readable by someone with the right instruments and the patience to measure it, telling a story of atmospheric events that occurred before the dinosaurs were gone, before the mammals that would eventually produce something like a human being had begun to diversify into the forms that would carry life forward into the Cenozoic. The mercury does not know it is a record. The sediment does not know it is an archive. It simply is what it is. Atoms of mercury, once dispersed through the air by the heat of erupting basalt, eventually settled and buried and compressed into the stone that a geologist will one day core through with a drill in a distant ocean, lift to the surface, carry to a laboratory, and read. And it is to the youngest of these great lava provinces that we turn now, because it is the one we can still walk across, still touch, still trace with a fingertip along the layered face of a cliff above a river. The Columbia River Basalt Group is not ancient in the way the Deccan is ancient, not remote in the way the Siberian Traps are remote. It is geologically young, sitting in the Pacific Northwest of North America, and it is extraordinarily well preserved, which makes it the window through which geologists have learned to read the older, larger, more ruinous floods that came before it. The eruptions of the Columbia River Basalt Group began roughly 17 million years ago, and the most intense phase lasted from around 17 to 15 million years ago, with activity continuing at a reduced pace all the way to about 6 million years ago. In that span of time, lava flooded an area of roughly 210,000 square kilometers across what is now Washington, Oregon, and Idaho. The total volume of rock is estimated at around 210,000 cubic kilometers. These are numbers that resist easy compression into anything the mind can hold naturally. But there is one fact from the Columbia River Basalt Group that does something the dry statistics cannot. It makes the scale felt. There were individual lava flows within this province that traveled from their source vents in eastern Washington and Idaho all the way to the Pacific Ocean. Not trickles, not thin fingers of cooling rock that crawled a few kilometers before hardening. Single eruptions, single discrete episodes of outpouring that sent molten basalt moving more than 500 kilometers across the landscape before cooling. 500 kilometers, the distance from London to Edinburgh, the distance from Chicago to Detroit, and most of the way back again, and they made that journey while still liquid over the course of days to weeks, moving across a terrain that would have looked nothing like what stands there today. Imagine, if you can hold it gently in mind before sleep carries it away, what it would mean to stand at the edge of such a flow. The sky ahead of you to the west is ordinary. Behind you, somewhere in what will become Idaho, the ground has opened, and basalt is pouring out of the earth at temperatures above 1,000 degrees Celsius. You would not see the source. You would only see the front of the flow approaching, a dark, viscous mass several meters high, moving not with the speed of an explosion, but with the slow, inexorable pressure of something too large to be hurried. The ground trembles faintly, the air ahead of the flow is warm, and then it passes and the world behind you is buried, and the flow continues moving west and west and west, until days or weeks later it reaches the sea. This is not folklore. This is not dramatization borrowed from a disaster film. It is what the rock record tells us happened, deciphered from the chemistry and distribution of the basalt itself, from the fossils entombed within and beneath the flows, from the absence of erosion between some layers that indicate successive eruptions came so quickly the landscape had no time to weather between them. The Columbia River Basalt Group has been studied with extraordinary care precisely because it is young enough to preserve these details, and what those details tell us is that the ancient flood basalts of the Deccan and the Siberian Traps were not anomalies, not singular, impossible events, but the larger expressions of a process the Earth still knows how to perform. The landscape carved into the Columbia River basalts gives some sense of what was buried. The cliffs along the Columbia River Gorge expose those stacked layers clearly, hundreds of meters of flat-lying basalt flows visible in cross-section as the river has cut down through them over millions of years. Each horizontal band is a separate flow, a distinct eruption laid down and then buried by the next. Some bands are thick, some thin. Some show the glassy, fractured texture of rapidly cooled lava. Others show the more columnar structure that forms when basalt cools slowly and evenly, contracting into the hexagonal columns that appear with a strange mathematical regularity at basalt formations around the world. The columns at the Columbia River Gorge, at the Giant's Causeway in Northern Ireland, at the cliffs of Fingal's Cave in Scotland, at dozens of sites across the flood basalt provinces of Earth, all formed by the same process: cooling, contracting, cracking, in the pattern that minimizes stress, arriving at the hexagon as the most efficient solution, as though the rock is reasoning its way toward geometry. Further east, in the region of eastern Washington, the landscape carries a different kind of mark. The channeled scablands, a terrain of dry river channels, cataracts, and scoured rock basins carved into the basalt by catastrophic flooding at the end of the last ice age, when ice dams failed and glacial lakes drained across the region in pulses of almost unimaginable force. The basalt was already there, waiting, laid down millions of years before the floodwater came. The scablands are basalt country. The rock underfoot, wherever you walk them, is the frozen remnant of those ancient lava rivers, and the channels cut through it expose the layering just as the gorge does, the same staircase of flows, the same record of a landscape remade again and again by material rising from the deep earth. What geologists find most valuable about the Columbia River basalt group is precisely this legibility, because the province is young enough that the rocks have not been deeply buried or substantially metamorphosed or eroded beyond recognition. The flows can be traced across the landscape, their source vents identified, their individual volumes estimated, their dates constrained by radiometric methods to a precision unavailable for older provinces. The CRBG is, in a sense, the Rosetta Stone of flood basalts, a well-preserved example of a process that has operated across billions of years of Earth history, readable in enough detail that it becomes the template against which the older, larger, more catastrophic events are interpreted. This is how geologists approach the Deccan Traps and the Siberian Traps and the provinces that came before them. They look at the young, clear example. They map its flows, measure its chemistry, determine how fast individual pulses arrived, how long the quiet intervals lasted between them, how the gases released by the eruptions would have interacted with the atmosphere of the time. And then they apply what they learn carefully and with appropriate uncertainty to the record preserved in the older, more degraded provinces. The Columbia River Basalt Group is the laboratory. The others are the archive to which the laboratory's lessons are applied. And even in this younger, smaller province, the signal of what flood basalts do to the air is detectable. There is a coincidence of timing between some of the more intense episodes of Columbia River volcanism and shifts in the climate record of the Miocene epoch, shifts in temperature and in the chemistry of the ocean that suggest even this relatively modest outpouring was sufficient to leave a mark on the world's atmosphere. Not a mass extinction, not a great dying, but a fingerprint legible in the isotopic and chemical record of sediment cores of the same process that in its larger, older, longer expressions has repeatedly coincided with the worst moments in the history of life on this planet. There is one more province that must be named before this account can reach its close, and it is perhaps the least known of all, the most hidden, and in some respects the most astonishing. It sits beneath the surface of the southwestern Pacific Ocean, far from the Solomon Islands, and it has a name that does not appear in most textbooks and that most people who have not studied geology will never have encountered: the Ontong Java Plateau. It is, by the best estimates of the geologists who have spent careers trying to measure it, the largest known oceanic large igneous province on Earth. It may be the largest single volcanic structure the planet has produced, and it is almost entirely invisible because it sits beneath the sea. The plateau formed primarily between roughly 120 and 125 million years ago in the early Cretaceous, at a time when the dinosaurs were not yet extinct and the continents were arranged differently, and the configuration of ocean and land was substantially unlike what exists today. Eruption after eruption of basalt poured out onto the seafloor in the southwestern Pacific, building the crust upward until it reached a thickness that normal oceanic crust, formed at the spreading ridges where plates pull apart, never achieves. Normal oceanic crust is roughly 7 kilometers thick. The crust beneath the Ontong Java Plateau is, in places, more than 30 kilometers thick. It is as though the sea floor in that region was built up to nearly continental thickness, not by the slow, steady spreading of a ridge, but by the extraordinary, sustained outpouring of a mantle plume meeting the base of the lithosphere and sending vast quantities of molten rock to the surface. The total area of the plateau is roughly 2 million square kilometers. To hold that in comparison, Alaska, the largest state in the United States, covers about 1.5 million square kilometers. The Ontong Java Plateau is larger than Alaska. It covers nearly 1% of the entire surface of the Earth, and it sits mostly submerged on the floor of the Pacific, rising in places close enough to the surface to form islands. The Solomon Islands themselves are, in part, the expression of the plateau's elevation, but largely invisible, known only through the oceanographic surveys that have mapped the seafloor's topography and through the drill cores that have brought samples of the rock to the surface for analysis. The volume of basalt locked within the Ontong Java Plateau is estimated in the tens of millions of cubic kilometers, not thousands, tens of millions. If you were to take all the rock of the Deccan Traps, which is already enough to bury the continental United States under hundreds of meters of basalt, you would need to repeat that exercise not once, but many times over to approach the volume of the Ontong Java Plateau. The numbers lose their grip on imagination at these scales. They become more like gestures toward magnitude than precise claims. But even as gestures, they communicate something real, that the Ontong Java Plateau is the largest outpouring of volcanic material from the interior of this planet that we have so far been able to identify, and that its formation 120 million years ago was an event of truly planetary consequence. The connection between the Ontong Java Plateau's formation and conditions in the ocean during the early Cretaceous is real, but, as with so much in this field, honestly debated. The period around 120 million years ago is marked in the sediment record by what are called oceanic anoxic events, episodes during which large portions of the ocean lost their dissolved oxygen. The ocean, in normal conditions, circulates oxygen through its depths. The surface waters in contact with the atmosphere are oxygenated, and this oxygen is carried downward by the slow overturning of deep circulation. But during oceanic anoxic events, this system was disrupted and the deep ocean became starved of oxygen, and in those oxygen-free waters, organic material accumulated on the seafloor without decomposing, preserved in the black shale that geologists recognize as the signature sediment of these episodes. The eruptions of the Ontong Java Plateau are a plausible driver for at least some of these anoxic events. The outpouring of carbon dioxide from the eruptions would have warmed the planet, slowing the circulation that carries oxygen to the depths. The nutrients released from the seafloor by the eruptions themselves and from the weathering of newly emplaced basalt would have fertilized the surface ocean, fueling blooms of marine life whose death and sinking organic matter would then have consumed what dissolved oxygen remained in the water below. The picture that emerges is of an ocean partially suffocated by the consequences of its own floor being remade from below. But this connection, while geologically reasonable and supported by the coincidence of timing, is not established with the certainty that would allow the textbooks to simply state it as fact. The causal links are modeled and inferred, not observed directly, because no one was present to observe them and because the sediment record preserves only indirect signatures of atmospheric and oceanic conditions. The oceanic anoxic events happened. The Ontong Java Plateau formed at approximately the same time. The mechanisms by which one might drive the other are coherent with what we know of ocean chemistry and atmospheric dynamics. Whether the connection is as direct as the correlation implies is still, as of our current understanding, a question held open. The same uncertainty applies to the question of how the Ontong Java Plateau itself formed. The dominant hypothesis is a mantle plume, a column of anomalously hot rock rising from deep within the mantle, perhaps from near the boundary between the mantle and the core, spreading out beneath the lithosphere as it reaches the base of the plate and releasing vast amounts of lava as it does so. This is the same mechanism invoked for the Deccan Traps, for the Siberian Traps, for the Columbia River Basalt group, for large igneous provinces generally, a plume head arriving beneath the plate, decompressing as it spreads, and producing an outpouring of magma on a scale that normal plate tectonic volcanism at spreading ridges and subduction zones does not approach. But there is a minority hypothesis genuinely present in the scientific literature, though not widely accepted, that the Ontong Java Plateau might have formed differently, that a bolide impact on the seafloor, an asteroid or comet striking the Pacific floor, could have triggered or substantially contributed to the eruption. The evidence for this hypothesis is sparse and contested. Most geologists who work on the plateau find the plume hypothesis adequate to explain what the rocks record, but the minority view exists, and it is worth noting because it sits in an interesting resonance with the broader story this account has been tracing. The question of whether catastrophe from above and catastrophe from below can interact, whether an impact can trigger or accelerate volcanic eruption, whether the sky and the ground work together in ways that the neat division of cause and effect cannot fully capture. This is the same question, in a different form, that the Deccan impact debate raises. The impact-triggered Deccan hypothesis suggests that the seismic energy of the Chicxulub impact, propagating through the planet's crust, may have accelerated the Deccan eruptions. It is a minority view for the Deccan too, but it refuses to disappear from the conversation because the timing is uncomfortable enough to notice. The most intense phase of Deccan volcanism in some chronologies coincides very closely with the impact itself. Whether this coincidence is coincidence or whether it reflects a real causal link between the collision and the eruption is exactly the kind of question that geology, reading the deep past from incomplete evidence, cannot yet definitively answer. What all of these provinces share, what makes them a coherent story rather than a list of separate curiosities, is the underlying process. The mantle plume, that great upwelling of heat from the deep interior of the planet, periodically delivering volumes of rock to the surface that dwarf anything produced by the familiar volcanism of erupting mountains and subduction zone vents. The plume rises slowly by geological standards, but by human standards it is not moving at all. It takes millions of years for a plume head to ascend from the deep mantle and begin to spread beneath the base of the lithosphere. And then, over hundreds of thousands of years, it releases its energy as lava, as gas, as heat transferred to the ocean and the atmosphere, as a reorganization of the chemistry of the air that living things breathe and the water they depend on. And this process is not unique to Earth. Basalt is the most common volcanic rock in the solar system. The floors of the oceans of this planet are basalt, generated at the spreading ridges by exactly the same partial melting of the upper mantle that drives flood basalts, though at smaller volumes and over longer, steadier timescales. The Luna Maria, the dark plains visible on the face of the moon on a clear night, plains that early astronomers named as though they were seas because they looked dark and flat and smooth from a distance, are solidified basalt. Vast flood basalt provinces erupted billions of years ago when the moon's interior was still warm enough to generate magma in quantity. The moon has been geologically quiet for 3 billion years, but the record of its flood basalts is written across its face in the dark material that fills the ancient impact basins. Venus, our nearest planetary neighbor, is covered in basalt plains. The surface of Venus is a landscape of flood basalt and volcanic constructs, reshaped by an interior that appears to have remained volcanically active far more recently than the Moon, perhaps even into geologically recent times by planetary standards. The same kind of mantle plume activity that built the Ontong-Java Plateau and filled the Deccan with lava may operate on Venus, may have periodically resurfaced that planet with basalt in episodes analogous to what Earth's large igneous provinces record. We cannot study Venus's basalt in the way we study the Columbia River basalt group because we have not drilled it, have not dated it with radiometric precision, have not mapped its individual flows with the resolution that terrestrial geology achieves. But the planetary process is recognizable. It is the same. This is what deep time reveals, if you follow the geology far enough, that the eruptions traced in this account are not accidents, not singular disasters, not the anomalous behavior of a planet gone briefly mad. They are the periodic surfacing of the planet's own heat. The Earth formed from the same cloud of gas and dust that formed the Sun and the other planets, accreting material over millions of years, and in the process of accretion it gained an enormous internal heat budget, some from the gravitational energy of material falling together, some from the decay of radioactive isotopes locked in the rock. That heat has been slowly bleeding out ever since, through the ocean floor, through volcanoes, through the great slow movements of tectonic plates. The large igneous provinces, the flood basalts, the mantle plumes are part of that bleeding, concentrated, episodic, catastrophic to life when they arrive, but ultimately expressions of the same thermodynamics that keep the planet geologically alive. A single human lifetime set against this timescale would register nothing. If you were born in the middle of a period of mantle plume activity and lived for a century, you would not see the eruptions. The pulses of a large igneous province are separated by thousands of years. The entire province unfolds across hundreds of thousands of years. In a single century, in a single millennium, you would see only the quiet basalt plain, the rock underfoot, the distant stable outline of a basalt escarpment on the horizon, perhaps a trickle of water in a channel cut by some long-forgotten episode of erosion. Nothing that would tell you, without the instruments and the knowledge, that this landscape was made by fire that poured for longer than the entire span of human civilization has existed, multiplied hundreds of times over. This is the strangeness that the geologist lives with, that the landscape appears static, permanent, ancient in the sense of being fixed, and yet the record in the rock tells a story of repeated, catastrophic transformation. The basalt plain that looks as permanent as anything on Earth is itself the remnant of a catastrophe, cooled and quiet and patient now, but carrying within its chemistry the signature of the atmosphere it altered, the ocean it acidified, the species it helped erase, the mercury in the sediment, the shift in carbon isotopes across the boundary, the absence of species above the line that are present below it, and then on the other side of the ledger, the recovery, the slow, steady, gradual return of complexity and diversity and abundance to an ocean and a landscape emptied by the confluence of catastrophe. Life does not disappear from the record after the Deccan eruptions, after the Chicxulub impact, after the KPG boundary. It changes. It is diminished, then slowly, over millions of years, it diversifies again. The mammals that survived the end Cretaceous, small and generalist and numerous enough in their variety of form to find footholds in the emptied landscape, expanded into the ecological space vacated by the dinosaurs. The birds, which are the avian dinosaurs, survived and continued and are with us still. The ocean, acidified and warmed and oxygen depleted, slowly restabilized as the volcanism waned, and the CO2 that had been pumped into the atmosphere was gradually drawn down by the weathering of the same basalt that had released it, rock reacting with rainwater and pulling carbon out of the air and locking it into carbonate minerals washed to the sea. The basalt weathers. The planet breathes in what it breathed out. Over millions of years, the carbon budget restores itself, and the temperature of the ocean and the atmosphere drifts back towards something the surviving lineages of life can inhabit. This too is a part of the story. The flood basalt is not simply destruction, it is a disruption, an episodic reorganization of the planet's surface chemistry, after which the chemistry slowly heals. The question that remains open, the question that keeps the Deccan asteroid debate alive and the Siberian Traps research active and the Ontong Java studies ongoing, is the precise degree to which volcanic outgassing versus impact energy versus a combination of both is responsible for any given episode of mass extinction. And that question remains open because the answer, honestly pursued, is not yet available. Lie with that uncertainty for a moment if you can. Not the frustration of an answer withheld, but the comfort of a question genuinely held open by careful people working with incomplete evidence, who publish opposing chronologies in the same journal in the same year, who measure the same rocks and arrive at different conclusions, and who return to the field and the laboratory and the sediment core to measure again. The uncertainty is not a failure of the science. It is the science doing what it does, approaching an asymptote, getting closer and closer to an answer without, so far, quite reaching it. What we do know firmly and without serious challenge is that large igneous provinces are real, that they are the largest volcanic phenomena in the geological record, that they coincide in time with the major mass extinctions across the past 250 million years, that the kill mechanism they provide, with the whipsaw of sulfur cooling and carbon warming and acid rain and ocean acidification, is chemically coherent and geologically supported, and that the planet has produced them repeatedly, from the Siberian Traps to the Deccan to the Columbia River Basalt Group, to the hidden enormity of the Ontong Java Plateau resting on the floor of the Pacific. They are not accidents, they are features. They are part of how this planet manages its internal heat, and they have shaped the history of life on its surface as surely as the slow accumulation of evolutionary change across the quieter intervals between them. There is something in this, if you let it settle quietly, that is not frightening. Or not only frightening, there is something in it that is vast in the way that deep sky is vast, or deep water is vast, or deep time itself is vast, a dimension so far beyond the ordinary scale of human experience that the mind, rather than being crushed by it, can float in it, weightless, unbothered by the small anxieties of the day. The Deccan eruptions that may have helped unmake the Cretaceous world began 66 million years ago. The Ontong Java Plateau formed 120 million years ago. The Siberian Traps that ended the Permian erupted 252 million years ago. And the Earth before all of that was already old, already shaped by billions of years of cooling and flowing and reshaping and cooling again before any of the creatures we would call familiar had yet evolved. Against that span of time, a single human life is not even a geological moment. It is less. It is the kind of duration that the geological record cannot resolve, cannot detect, the kind that vanishes between one sediment lamination and the next. And yet here you are, inside it, at the end of this particular day, with the weight of the day already beginning to lift, and the floor of the Pacific resting beneath 30 kilometers of cold basalt, and the Columbia River Gorge holding its stacked record of ancient lava in the dark, and the Deccan Plateau sitting quietly in west-central India with its 2-kilometer pile of stair-stepped rock, and the question of what killed the dinosaurs still genuinely open in the pages of peer-reviewed journals, waiting for more evidence, more precision, more cores drilled, and isotopes measured, and chronologies refined. It is all still happening slowly in the way that geological things happen. The mantle plumes are still there, still moving, still delivering heat, toward the surface. The seafloor is still spreading at the ridges, still carrying the oceanic plates toward the subduction zones where they descend again. The planet is still breathing, still managing its heat, still occasionally making lava in quantities that would, if they arrived in a concentrated enough pulse, reshape the air and the ocean and the history of whatever life happened to be living through them. But tonight, none of that is arriving. Tonight, the basalt is quiet. The mercury has long since settled into the stone. The whipsaw of sulfur and carbon has run its course across the millions of years, and the chemistry of the ocean has stabilized, and the birds, which are the survivors, are quiet in the dark outside, and the moon, with its ancient basalt Maria shadowing its face, is somewhere above the clouds, and the earth is doing what it does in the long intervals between catastrophes, holding steady, weathering slowly, sustaining the improbable, fragile, persistent experiment of life across its surface. If you feel moved to leave a word in the comments where you're listening from tonight, what corner of this basalt planet you happen to be resting on, I would genuinely like to know. The comments are there, and I read them. It means something to know where these slow stories find their listeners, which cities, which countries, which quiet rooms at the end of which days. There are more stories here of the same slow and careful kind, waiting for whenever you want them. Stories of other deep times, other deep places, other questions that the record in the rock holds open and patient. But for tonight, this one is done. You have followed the lava from Idaho to the Pacific, across the face of the Deccan Plateau and the floor of the southwestern Pacific, through the chemistry of the air and the sediment and the stone. You have held the uncertainty of the great debate without needing it resolved. That is enough. That is more than enough for one night. Put down whatever remains of the day. Let the Ontong Java Plateau rest on the floor of the Pacific, 30 kilometers of basalt between you and the deep mantle. Let the Columbia River Gorge hold its stacked flows in the dark of the Pacific Northwest. Let the question of the sky and the ground and the dinosaurs stay open in the good hands of the people working on it, while you are not working on anything at all. Tie off here at the Wisdom Docks. The tide will wait till morning. Good night. Sleep well.